In earlier lessons, we had talked about the development of what we might call Newton's universe, at least our Newtonian picture of the physical universe from the uh, development of Copernicus' heliocentric model to Kepler's development of laws to Newton's synthesis of all of this into a picture of a single united universe. And the key features of Newton's picture of the universe were these. The world is governed by predictable natural forces. That was a major idea we talked about. But when considering time, time was understood by Newtonian physicists, classical physicists, as simply the progression of the activities of matter and forces in emptiness, essentially emptiness. Three-dimensional space has length, width, and height, but it's really not a thing. It's just empty space. And of course, space and time will be absolute, meaning that they never change depending on what people are doing. They're always the same for everyone. 1 second is 1 second, no matter who you are or where you are or what you're doing. 1 meter is always 1 meter, no matter where you're measuring it. Because of course, space is nothing, and nothing can't be different for different people. And of course, since time is simply the progression of activities of matter and forces, well, those activities are independent of what human beings do and how human beings see them. And so both time and space will be absolute and unchanging for everybody. But there was a hint that classical physics had come up with that suggested that maybe that picture of the universe, of space and time, might not be that simple. And that's something we've already talked about. When we started talking about electromagnetic radiation, we said that light is an electromagnetic wave that always travels through empty space at 300,000 kilometers per second. Now, the real key word here that upset our entire picture of the universe is this one word, always, because light is an electromagnetic wave that always travels through space, through empty space at 300,000 kilometers per second. Always, always, always. And not only did this seem to have been experimentally verified, but in 1867, a Scottish physicist, James Maxwell, developed the equations for electromagnetic radiation, and the equations showed clearly that electromagnetic waves must always propagate through space at 300,000 kilometers per second. Always. Well, this is a bizarre conclusion. And you probably don't see why it's so bizarre, but let me try to explain that to you. In a Newtonian universe, speeds should always be additive. Well, what does that mean? Imagine here is the Earth. Imagine that there are two asteroids that are heading towards Earth, and they're both going to be exactly the same size, exactly the same mass. This is not a trick question. Here's asteroid A, and it is heading towards the Earth at the speed of 35 kilometers per second. Here's asteroid B, which is again the same mass, and it's heading towards the Earth at 35,000 kilometers per second. Which asteroid, if it hits the Earth, will do more damage? Well, they're the same mass, they're moving at the same velocity, and so the first conclusion would be that they would do the same amount of damage. But what we've left out of this is the fact that the Earth is also moving. Let's say it's moving in this direction at 30 kilometers per second. So now if we want to know how fast these asteroids will be moving relative to the Earth when they hit, we need to actually look at both of these speeds, the speed of the asteroid and the speed of the Earth. So for asteroid A, it's moving towards the Earth at 35 kilometers per second, but the Earth is also moving away from the asteroid at 30 kilometers per second. So the net speed when that asteroid catches up and strikes the Earth is going to be the 35 kilometers per second of the asteroid minus the 30 kilometers per second of the Earth, or we could say plus the negative 30 kilometers per second because it's moving away from us. So the net speed will be 5 kilometers per second when that asteroid hits the Earth. What about for the other asteroid? Well, it's moving towards the Earth also at 35 kilometers per second, but because it's coming from the other direction, the Earth is moving towards it at 30 kilometers per second. So the net speed when they collide will be the 30 kilometers per second of the Earth plus the 35 kilometers per second of the asteroid for a net speed of 65 kilometers per second. The point here is that when objects are moving relative to each other, according to classical physics, their speeds need to be added together to get the total relative speed. But this doesn't seem to happen with light. The speed of light should not be constant for observers moving relative to one another, according to classical physics. Let's look at the same scenario here, but now instead of asteroids, we have beams of light that are coming from two different stars. For this star over here, star A, that beam of light coming from that star is traveling through space at 300,000 kilometers per second towards the Earth. For star B, the light is also traveling at 300,000 kilometers per second through empty space. But now do we not have to take into account the motion of the Earth? Because for this beam of light, the Earth is also moving away from that star and that beam of light at 30 kilometers per second. So according to classical physics, the speed that we would measure for that beam of light coming towards us, just like with the asteroid, should be the speed of light minus the speed of the Earth's motion. So 300,000 kilometers per second minus 30 kilometers per second should give us a speed of light measured from this star as 299,970 kilometers per second. Conversely, since this beam of light is moving towards us at 300,000 kilometers per second, and we're moving towards it at 30 kilometers per second, according to classical physics, the speed we should measure for this beam of light should be the 300,000 kilometers per second of the light plus the 30 kilometers per second of the Earth for a speed of light measured as 300,030 kilometers per second. But according to Maxwell's equations and according to observational results, both speeds are always measured as 300,000 kilometers per second. Regardless, it's like this motion of the Earth somehow didn't matter, or somehow this 30 kilometers per second, 30 kilometers is a measurement of space, seconds are a measurement of time, somehow this 30 kilometers per second is different from this 30 kilometers per second. How can that be? Space and time, according to Newton, are absolute. This is so weird that most scientists just assumed there must be a mistake in Maxwell's equations, that there's something we're missing. There was one scientist, however, one major scientist, there were a few others, but the one we remember today who took this seriously was this man. This is Albert Einstein in his pre-old man with crazy hair days. This is Albert Einstein around the year 1905. And what he said is that we've looked and we've looked and we've looked. Remember that Maxwell's equations were developed in 1867. We're now in the year 1905. So, sorry, about 38 years have gone by, and in all that time, physicists were unable to find any flaw in Maxwell's equations. And so Einstein said, well, you know what? We have to trust the math. Math is our most certain, most precise source of knowledge. Numbers, quantification is the way we keep ourselves from being fooled by our senses. So if the math says something and we can't find a reason to deny it, then we have to take it seriously, even if it violates our common sense. So what he did was he went with the idea that maybe the speed of light really is constant, the way Maxwell's equations say. Maybe that's correspondent truth. What does that tell us about the universe?